Rational inequalities. We've learned how to solve several different types of inequalities. Rational inequalities are similar to solving polynomial inequalities. So we have two methods. We can solve by graphing or we can solve with a sign chart, and we're going to go through both types. When we solve rational functions by graphing, it's very familiar to us. We graph each expression on either side of the inequality as two separate equations or functions. Then we identify all of the points of intersection. So for example, we're going to solve 6 over x minus 1 minus 6 over x and determine where this function is greater than or equal to 1. So as we stated on the last slide, we are going to solve this rational inequality by entering the left-hand side as one function. So y1 is going to be 6 over x minus 1 minus 6 over x. And then our y2, or our second function that we put in there, is just y equals 1. So we can see it graphed in this -5 to 5 window for the x and y. And since this inequality asks for when this function is greater than or equal to 1, we're looking for where the function is above and also intersecting the line y equals 1. So the first intersection point is at -2, 1, and the other intersection point is at 3, 1. So we're within this interval from -2 to 3, including the endpoints because of the equal to, such that x cannot equal 0 and x cannot equal 1. Well, why is that the case? Well, the reason why x equals 0 and x equals 1 are not included is because that's where the rational function equals 0 in the denominator or is undefined. So because the function's undefined at x equals 0 and x equals 1, they are not included in this set. So another way to write this section of the graph is that x is contained in the interval from -2 to 0, including -2, in union with 0 to 1, in union with 1 to 3, where 3 is included. Now, if you notice, when we look at this graph, there's this gap in the middle here. So I have a feeling that our function's missing a piece in the coordinate plane. So let's zoom out of our graph to make sure that this is the correct solution. And if it's not, we can make a correction to it. Let's see what happens when we zoom out. So if we actually zoom out of our previous graph that we had, which only went from -5 to 5 in all directions, we see that there's a little piece of the graph that's missing. There's this tiny sliver that starts off at like -infinity, hugs x equals 1, and then comes to this point at 1/2 -24, and then it curves and goes right back down. So now this tells us that this middle interval from 0 to 1 that we originally had should not be included in our final solution set here, or interval set. And that's because from 0 to 1, it's not above the line y equals 1. So it should not be included in our answer. Therefore, the final set of numbers that satisfy the conditions of this inequality is x is contained in the interval, including -2 up to 0, not including 0, in union with 1, where we're not including 1, up to 3, where we are including 3. Now let's look at how to solve rational inequalities using a sign chart. This method has slightly more steps. However, it's more practical in most cases, especially when a calculator for more complicated inequalities is not available. It's also a method that you're going to end up using a little bit more when you get into calculus, whether it's honors or AP or in college. Because when you're talking about calculus, you're going to be finding critical values of a function and then determining the function behavior based on some signs and stuff like that. So this is kind of a precursor to what you're going to be doing a little bit more next year or in the next course. So here are the steps that are going to help us. First step, move all of the terms to one side. this will make one side of the inequality have 0 in it. So you'll have some sort of rational function is related somehow to 0. Next, you're going to factor both the numerator and the denominator. Then the zeros of the numerator and denominator are critical values. Well, why? Well, the numerator, if the numerator is set equal to 0, that's when the function's going to be equal to 0, or it'll give you your x-intercepts. And then the denominator, if any of those values are equal to 0, those are going to give you your asymptotes or holes or discontinuities that exist in your rational function. Then we're going to make a number line with all of these critical values plotted with some space in between. And then we're going to test values in between these critical numbers to determine if the function is positive or negative in that interval. And then based on our answers, like whether we have positive or negative outputs, we can then identify the solution intervals of where the rational function is either greater than, less than or equal to, or greater than or equal to 0. So again, we're going to use these steps to help us determine what the function behavior is. Let's try an example. So our example is this function, x squared minus 4 over x squared minus 4x is greater than or equal to 1. We're going to start our example by getting one side equal to 0. So the original one that we had to begin with was x squared minus 4 over x squared minus 4x was greater than or equal to 1. So we've got to take this 1 and we have to subtract it to the other side to get this inequality related to 0. So that was the first step that we did right here. We subtracted 1 to both sides. Now it's in relation to 0. In order to determine our rational function, our final one, we have to have a common denominator, which will be x squared minus 4x. And if you'll remember, any expression over itself is equal to 1. So you can rewrite this expression as x squared minus 4 minus x squared minus 4x all over x squared minus 4x. So in other words, let me change my color really fast. Let's make it blue. So I'm taking 1 and I'm multiplying it by x squared minus 4x over x squared minus 4x. And that's how I got this expression right here. And again, it's still greater than or equal to 0. And then if we distribute the negative 1 that's outside of these parentheses into both terms that's here, we're going to end up having x squared minus 4 minus x squared plus 4x. Make sure that when you distribute this negative 1 through, the sign changes there. And then all over the denominator x squared minus 4x. And then you'll note, oh, I have an x squared here and I have a negative x squared here. They cancel each other out. So they're going to go away. And that leaves me with this rational expression, negative 4 plus 4x over x squared minus 4x. We can also factor. If you notice the top, we have a common factor of 4 here. I can pull it out. And when I do that, I would get 4 times negative 1 plus x. Using the commutative property, you can swap these two around and get x minus 1. And then in the bottom, we can factor out an x, and you're left with x minus 4. So here is our factored form of our rational function. And it is greater than or equal to 0. We're going to have critical values of 0, 1, and 4. How did we get those? Well, first let's look for the asymptotes. The asymptotes are when the denominator is equal to 0, so that's when x is 0 and when x is 4. So that takes care of these two. And then the other critical value is the x-intercept, and that's where the numerator is equal to 0. So if x minus 1 is equal to 0, the x value is 1. So that's how we get our 3 critical values, and we're going to put them on a number line. They don't necessarily have to be equally spaced, and clearly here they're not. Like it doesn't have to be a perfect scale. And then just select some values that are in between. They can be random. I try to use easy numbers like 1, -1, 0 when those are not the critical values. Since 0 and 1 are critical values, I can't exactly use them. So we'll do -1 as the number that we're going to substitute in here. We can do 1/2. That's kind of easier. And then 2 in between here and here, and 5. So what we're going to do is we're going to substitute these values into our rational function and see if the output is positive or negative. Okay, so the exact value that these test points provide doesn't really concern us. We only care whether the values in between our critical numbers that we have here, whether they're positive or negative. So let's actually start by rewriting that inequality. When it was in simplified form, it was 4 times x minus 1 over x times x minus 4, and this rational function is greater than or equal to 0. And again, we found that the critical values were 0, 1, and 4. So we selected -1, 1/2, 2, and 5 as x values that are in between, or our test points. If we substitute -1 in here, -1 minus 1 is -2, so it's negative value. -1 outside here is negative, and -1 minus 4 is -5, so it's also negative. So the 2 negatives in the bottom cancel each other out, so I have a negative over a positive, which is a negative number. This means that our rational function will be below the x-axis or less than 0. Now let's try 1/2. If I put 1/2 in, we get 1/2 minus 1, which is -1/2, so that's negative. The 1/2 itself out here is positive, so that's where we get this. And then 1/2 minus 4 is -3.5 or -7/2, which is negative. A positive times a negative is a negative, and a negative divided by a negative is a positive. So this is where the function is above the x-axis, or where its y outputs are positive. So where it's greater than or equal to 0. This one works. So this is going to be part of our answer. We'll come back to it again shortly. Now let's try our next test value, which is x equals 2. So 2 minus 1 is 1, so that's positive. We have a 2 out here, which is positive. So that's how I got those two. And then 2 minus 4 is -2, which is a negative number. So in the denominator, a positive times a negative is a negative, and then a positive divided by a negative is a negative value. This means that our y output at x equals 2 is below the x-axis, or the function is less than 0. Now let's try our last test point, which is x equals 5. 5 minus 1 is 4, that's positive. 5 itself is positive, and then 5 minus 4 is 1. That's also positive. So 3 positives give us a positive divided by a positive, which is positive. This means that the y output is above the x-axis, or the function is greater than 0. So this also works to satisfy our inequality. So now we have to convert these intervals that we found into a solution set, or a solution interval. So it goes from 0 to 1. We do not include 0 because that's one of our asymptotes. We do include 1 because that is an x-intercept, or where it crosses the x-axis. It also satisfies this inequality because it's allowed to be equal to 0. So that's why we include 1 here. And then we're going to put that in union with, from 4, that's an asymptote, so we do not include that endpoint value all the way up to infinity. So that's how we get this interval as our final answer to this question.